So at the end of the 19th century, a lot of new results were coming out of physics. Radiation was being discovered. There was something weird that was seen in the black body radiation spectrum that Planck was looking at. There were some interesting results that were coming out of electricity and magnetism, and it wasn't clear how those were going to be able to be absorbed into classical mechanics without some major changes. Of course, we know now that this was associated with the beginning sparks of quantum mechanics, along with special relativity, both of which led to epic changes in classical theories. But partly for those reasons, thermodynamics was also reassessed at the end of the 19th century, and it was found that there were some assumptions that had been made that were not properly accounted for. And so that required us to introduce the so-called zeroth law of thermodynamics, because we already had a first law and a second law, but this one actually had to come first. And this was a statement that really allows us to define a temperature. All right? What it says is that if substance A is in thermal equilibrium with substance B, and substance B is in thermal equilibrium with substance C, then substance A will be in thermal equilibrium with substance C. So this means that if I were to take substance A, put it into thermal contact, so allow it to exchange energy with substance B, there will be no net exchange of energy between substances A and B. Substance A will give substance B the same amount of energy on average as substance B gives substance A. So there's no net exchange of energy. In a situation like that, substance A and substance B are said to be in thermal equilibrium. No net flow of energy between them. So substance A and substance B are in thermal equilibrium. Substance B and substance C are in thermal equilibrium. Then substance A and substance C will be in thermal equilibrium. That's the statement of the zeroth law. It essentially says that thermal equilibrium is independent of what the substances are. It is important to make this statement because not all equilibriums satisfy this sort of transitive property. For example, chemical equilibrium exhibits flagrant violations of this transitive property. All right, as an example, you could have a hot sample of sodium metal in chemical equilibrium with helium gas, and that same helium gas in chemical equilibrium with a sample of chlorine gas. But despite that fact, if you put the hot sodium into chemical contact with the chlorine gas, you'll find that they are certainly not in chemical equilibrium with each other. Okay? So we needed to state that there is something called thermal equilibrium. This also allows us to define a temperature as a thing that is the same when objects are in thermal equilibrium. The first law states that energy is conserved The first law can be thought of as saying what can happen. All right? We need to have processes that conserve energy. But the first law by itself is not enough. Because if I take, for example, a cup of boiling water and I put 2 ice cubes in it and then walk away for an hour, I would expect to find a cup of warm water. If, on the other hand, I put a cup of warm water on a counter and walk away for an hour or two and come back, I would not expect to find a cup of boiling water with 2 ice cubes floating in it. Despite the fact that that transition, warm water to boiling water with ice cubes floating in it, is not at all in violation of the first law of thermodynamics. The energy is there. You could take a part of the warm water and pull a bunch of heat out of it, turn it into ice cubes, and put that heat into the warm water that remains, make it boil. That is not in violation of the first law. Despite that fact, ain't gonna happen. All right? Because it is in violation of the second law. The second law tells us what will happen, as opposed to just what can happen. And we'll talk about that next week.